Hi, and welcome to the fifth and final lesson on connected particles. This time we're going to be looking at two objects connected by a string that runs over a pulley. It's basically the same as cars and caravans, except you can't model them as one particle altogether. Last time we looked at this problem here, and we were able to model it as one big object. This one, you can't really do that because they're moving in opposite directions. This one moves down, the other's moving up, and you can get into a bit of a pickle there. You might find that you can in some cases, but it's well worth not taking the risk most of the time. Key points, again, we need to assume not only the string is light and inextensible, but also that the pulley is light. This means that as it spins, it has no mass, there's no momentum or force needed to get it moving. And the fact that it is smooth means that it doesn't even need to spin at all. The string can just pass over it freely without any friction or any other forces. It just means that the only forces we're interested in are those that are acting on the object rather than on the pulley. And this means also that the tension in the string is the same. So we can have the same T here as here. We're not having to have different T values. Again, allowing us to solve equations simultaneously because they have the same value. So let's have a look at this situation here. I've already started drawing a diagram for it. We've got this box, 70 kilos suspended by a light rope over the edge of a cliff and passing over some smooth pulley. Sometimes they might use the word peg, okay, a smooth peg, because it doesn't matter if it's smooth, it doesn't matter if it's rotating or not, it's just going to be smooth, so it doesn't, no friction involved. And so the other end is then tied to this object at the top of the cliff. We're told that it's 5 meters from the edge, and that it's accelerating with a known acceleration. So here we're going to have acceleration equals 0.3 meters per second squared. And same again up here, that's going to be accelerating with 0.3 meters per second squared. This gives us the ability to form simultaneous equations. Again, we're going to have the tension being the same in both of these ropes, and we're also then going to need the weight of this. The weight of this one will be countered by the normal reaction, but we're not going to have to worry about that because it's just going to be moving left and right. But we are going to be interested in some friction. So let's come over here to our diagrams of the separate objects so that it can just be a little bit clearer what's going on with each object. So first of all, for the 120 kilogram one, we're going to have the tension pulling it to the right and friction pulling it to the left. We don't know what the value of either of those are. We could put on our weight and the normal reaction, but we won't be using those in the question in the rest of the solution. Over here, we've got 70 times G newtons as the weight, and this time the tension in the cable is the same tension. We're also going to want to mark on our direction, so this one is accelerating with 0.3 meters per second squared, and this one is accelerating again with 0.3 meters per second squared. In each case, let's take those as our positive directions. Okay, I've got two separate scenarios going on, so we can take two different directions. So then let's apply F equals ma, Newton's second law. And we're going to be doing this horizontally for this one here, and vertically for this one here. So first of all, for the red one, let's do T minus tension minus the friction will be equal to the mass times the acceleration. And we can't really go anywhere with that. We've got two unknowns. So let's come over to this one and see if we can get any further with this. Positive, we've got 70G. Negative, going upwards, we've got tension. Mass is 70 times acceleration 0.3. Now this one we can solve. So let's rewrite this as 70G minus 70 times 0.3 T. So we're going to get a tension of 679 newtons. Does it ask? It doesn't ask for the tension, therefore, and we don't really need to round up, but if it were, I'd need to round this. Now, I've used G, or it asks us to use G as 10 meters per second squared. So I have to round this to one significant figure, because otherwise I'm claiming more accuracy than I actually know. But for my solution of the next part of the question, I'm going to be using the unrounded value so that I'm not introducing more error essentially into my answer. So over here, I can now plug T as 679 minus, let's rearrange this to give us 120 times 0.3 equals friction. And so we're going to get a value of friction as 643 newtons. However, again, we need to round it as we do over here, so that's a different figure. So we're going to get friction equals 600 newtons to one significant. And there's our answer for find the magnitude of the friction force on the 120 kilogram box. Okay, that's the first part. The second thing it asks for is the speed when it hits the pulley. So this I'm going to label A, and over here we're going to put in here B. Okay, so how are we going to answer this? Let's just redraw the diagram. We've got this object here. We now know its, well, we know its acceleration. We now know the frictional forces, but they won't matter anymore. We just know that it's accelerating in this direction in 0.3 meters per second squared. It's got a distance of 5 meters to travel, and we're interested in the velocity or speed at the end. So here we're not talking about forces anymore. We're interested in speed. So we're going to be looking at the constant acceleration formula. So S U V A T, the distance is 5 meters, the displacement rather. It starts from rest. The crate is moving downwards. Yeah, I haven't explained that, but actually I should have written in the question that we assume that it starts from rest. So we'll put that in there. And then V is what we're interested in. Acceleration we know to be 0.3. T we don't care about. So we need to pick a suitable equation. And in this case, it's V squared equals U squared plus 2A. And all we have to do now is substitute in our values. So we're going to get 0 plus 2 times 0.3 times 5. And so we're going to get V equals square root of 3. So V equals 2 meters per second to 1 significant. And so note here that you might need to use both our understanding of forces and our understanding of constant acceleration. Have a go at this problem here. Sorry, let's make that a bit more readable. There we go. Have a go at this problem here. Pause the video, see what you can do. I've already started the diagram. Take your time. So here's my solution. Let's see what we can do. So this problem is significantly harder than the last one. Part A, I think you'll be okay with, a bit of simultaneous equations. But part B and C take a little bit more thinking, certainly C. So let's start with A. And that's what we're working on here. Okay. So we've got our separate diagrams. We're going to apply F equals ma to both. This one here is moving upwards with some acceleration that we don't know, and this one here is moving downwards with some acceleration. So we're going to take those as our positive directions, okay, for each of those objects separately. So here we're going to get t minus 1.9g equals 1.8, and over here we're going to get 3.5g minus t equals 3.5a. These are simultaneous equations. We can rearrange them so we can plug them into our calculator. So we're going to get t minus 1.9a equals 1.9g, which is 18.62. We're taking here g to be 9.8. Over here, we're going to get something similar. 34.3 is equal to 2 plus 3.5. Okay? Plug that into your calculator, and you'll get values for t to be 24.207 newtons, and the acceleration to be equal to 2.9407 meters per second squared. We do need to give this as to an appropriate degree of accuracy, so two significant figures because g is two significant figures. So we're going to say t is 24 newtons to 2sf, and acceleration is 2.9 meters per second to 2s. So there's our answers to part A. Okay, extension, part. I've got two A's and B's. Sorry, there's A. We're going to relabel that B, and I'm going to relabel that C. So here, part B, we're being asked to find the speed of B when it reaches the ground. So here, B has got 1 meter to fall, and we now know the acceleration of that. So we're going to use SUVAT, constant acceleration formula. So we've got 1 meter to go. We're starting from rest, so we're going to get initial speed of u, as well as 0. We're interested in the final speed. We know the acceleration is 2.9407 something. We're going to use a more accurate value than just 2.9. And t we don't care. So we're going to want, again, v squared equals u squared plus 2as. Type that in, plug it in, and we're going to get 0 plus 2 times 2.9407 times 1. And so we get v equals 2.425 meters per second. So v equals 2.4 meters per second to two significant figures. Hopefully that's relatively straightforward, but the next bit requires a bit more thinking. How are we going to answer this? Let's come down here, draw ourselves a new diagram. We'll keep those values there. Okay, so first of all, this object, A, will first of all rise 1 meter. Okay, so just come up here. It's going to rise 1 meter. As this rises, as this falls 1 meter, that's going to rise 1 meter. But then it's got an extra 0.2 meters to rise until it hits the pulley. So we've essentially got 2 stages to this before it hits the pulley. Okay. And in this section here, we know that it's accelerating upwards with A equals 2.9407 meters per second squared. But on this section, what's happening? Well, as this object hits the ground, it's not going to travel any further, but this object will keep going. It's going to keep rising up, which means the string is going to go slack. So there's no more tension. The only force acting on A from here on up, okay, well, no more tension, it's just going to be the weight pulling it down. Here we had tension pulling it up and the weight pulling it down. So here, this is essentially going to be under free fall, i.e. acceleration will be minus 9.8 meters per second squared. Acceleration due to gravity. Okay. So we're going to model this in two sections. I'm going to call this A, B, and C. So the journey from A to B, okay, is much like this journey over here that we've already calculated. Okay, but it's something that we haven't yet calculated. So we haven't calculated the time, so we need to calculate the time. So from A to B, we've got S equals 1, U equals 0. We've already worked out the speed from the previous question to be 2.4, or more precisely 2.451, blah, blah, blah. And then the acceleration is 2.9407, blah, blah, blah. And T is what we're in. Pick the simplest equation to solve this. I think V equals U plus AT will give us the easiest way of doing it. So V minus U over A equals T. And we're just going to substitute this in. So we're going to get 2.4251, subtract 0, divided by 2.9407 equals T1, because that's this here, T1 from there to there. And so we get T1 equals 0.824687, something. Not all those digits will be accurate because I'm rounding, but enough of them to be accurate, that's fine. We now need to work out the time difference from B to C, the last 0.2 meters. So I'm going to call that T2. I'm going to go from B to C. So here we're going to have S equals 0.2 meters. U, we know, is the final speed of the previous section. So the final speed here will be the initial speed here. So we're going to get 2.4251. V, we don't know, and we're not interested in. A, we now know is minus 9.8 meters per second squared, and T is what we're interested in. This time we have to use S equals UT plus a half AT squared. And we just need to substitute the values in. 0.2 equals 2.4251 T minus a half times 9.8 T squared. And we can type this into our calculator to solve for us, and we're going to get T equals 0.390356 was my calculator, and T equals 0.18456. Okay, so which of these two solutions do we want? Why have we got two? The reason we've got two is we've got this object here. We're trying to find out how long it takes to travel 0.2 meters. And it does that by rising and then falling. And so we get 2 times when it reaches that height. And we want the first time that happens, therefore T equals 0.1. And so the total time is going to be T1 plus T2 to give us 0.929 seconds, i.e. T equals 0.93 seconds. 2 significant times. And there is our full solution. That's a little bit small there, but hopefully you can see that that last section is really quite a hard extension. The key part is this first bit up here that you need to be able to do. Let me just go back into the top. So that part there, that's the main part you need to be able to do. Do feel free to pause and make notes if I've gone through that too quickly. So finally, this is the last part of exercise 19. Have a go at exercise 19E. Minimum, you want to be looking at questions 1 to 6, but do have a go at the others as well. And once you've done that, you need to try next practice 19. Okay. Have fun, take your time on these, and please ask questions if you're stuck.